In Chapter 6, we start working with inverse functions. Now we're going to look quickly at the graph of an inverse, but we are not going to have to graph one by hand. I'm just going to show you what it looks like. But we start with a review of inverse functions from college algebra. It says in previous sections, but the sections you learned about inverse functions were, again, college algebra sections, where we did the switch and solve. There are three basic things, though, that are true for all functions and their inverses. If I take the composition, and that's what this first one is, it's showing the composition of functions. If I take the composition of the function with its inverse in either direction, I get x, the argument, for every x that is in the domain of both f and the inverse. So let me go ahead and complete that notation. The other thing that is always true for a function and its inverse is that the domain and range are switched. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. A third thing that is true for all functions and their inverse is that the graph of the two are reflections with respect to the line y equals x. This book adds a fourth, that if the function y equals f of x has an inverse function, I can invert anything, but the inverse is only a function if I start with a one-to-one equation, a one-to-one function. If a function y equals f of x has an inverse function, then the equation of the inverse function is x equals f of y. This is my switch and solve. You learned how to use switch and solve in college algebra to find a function's inverse. The solution of this equation is the inverse function of x. So this is how we explicitly define our inverse function. Okay, we're going to come up here and use our little white space just to show you, for example, if I were going to graph, let's say I graph this function. Well, it is going to, let's say it goes through the point 1, 1, and then it has a point 2, 4 up here. So 1 squared is 1, 2 squared is 4. That's part of a parabola, right? Well, the inverse of that is going to look like this, that also goes through the point 1, 1, but this point is 4, 2 instead of 2, 4. That shows both that I switch the x and y, and that my function and its inverse reflect across that line y equals x. So there are two different ways that we use the properties of an inverse function. Let's look at the switch and solve. That switch and solve method, just to remind you, if I start with f of x equals x cubed, that's a one-to-one function. It passes both the horizontal and the vertical line test. To switch and solve, I rewrite this as y equals x cubed, and then I literally switch the x and y so that I have x equals y cubed, and then I solve for y again. Well, to solve for y, I'm going to need to take the cube root of both sides, so that would give me cube root of x equals y, and then I just rewrite it in inverse notation. F inverse of x equals cube root of x. So that's how I use the switch and solve method to find an inverse function. Okay, let's do a little bit of an exploration here where we talk through how we find our inverse trig functions. Now, based on the definition of a one-to-one function, this sine function is not one-to-one because it is cyclical. It follows a cycle. It's cyclical, and that means it fails our horizontal line test. Right? A function has to pass the vertical line test, and a one-to-one function has to also pass the horizontal line test. So this is not one-to-one. If I draw a horizontal line, I'm going to repeatedly intersect my function in various places. This function has a domain of all real numbers. The only way we can take the inverse and end up with an inverse that is also a function is if we restrict our domain. Our domain starts as all real numbers. I can input any angle. But if we choose to restrict that domain until the function is one-to-one, sorry guys, one-to-one, we restrict our domain until we have a one-to-one function, then our inverse will also be a function. Now there are there's an infinite number of ways we could restrict the domain to make our function one-to-one. But historically, mathematicians have agreed that for our sine function, we're going to restrict our domain from negative pi half to positive pi half. If we restrict our domain from negative pi half to positive pi half, so that we are just looking at those function values there, then we have restricted it so that we have a one-to-one function. This is just this piece of our sine function. So we restricted our domain from negative pi halves to positive pi halves inclusive. Our range is still started, the restriction on the range of sine function range is always going to be between -1 and 1. Now, one thing that you want to make note of is that every trig function is restricted, inverse trig function is restricted to 2 quadrants. So all inverse trig functions are restricted to 2 quadrants. Now, which 2 quadrants depends upon which trig functions we're looking at. So think about our circle. We've got our x-axis and our y-axis. Now, cosine, which is what we're talking about here, is y-dependent, correct? Cosine is y-dependent. We're talking about sine, and sine is y-dependent. So this is our sine function, and if we think about sine, our definition for our sine function, it's y over r. So we are focusing on the y-axis. Well, my y-axis, my y-coordinate is positive up here in quadrants 1 and 2, and it's negative in quadrants 3 and 4. So when I choose to restrict it to 2 quadrants, I have to pick a quadrant where sine is positive and a quadrant where sine is negative. And we have chosen historically to pick quadrants 1 and 4. We go from negative pi half to positive pi half, so that we have picked a quadrant where sine is negative and a quadrant where sine is positive with our restriction. Now when we move on and talk about cosine, cosine is x over r. It focuses on the x-axis. My x-coordinate is positive in quadrant 1 and negative in positive 2. So if I choose the restriction from 0 to pi, I have included an x-coordinate that is positive in quadrant 1 and negative in quadrant 2. So the restriction for cosine is going to be different than the restriction for sine. All right, let's look at that next page. So how is the inverse of y equals sine x notated? Defined implicitly, the inverse sine function of y equals sine x is x equals sine y. That's when I do the switch. If I want to define it explicitly, I go ahead and solve, and what I end up with would be y equals sine inverse of x. Now, the sine inverse is a button on your calculator, and we're going to use that. So here's our definition where we see the graph of our sine function and our inverse sine function. We start with sine inverse. We've switched our domain and range. The domain of our sine function was all real numbers, but we chose to restrict it to negative pi half to positive pi half inclusive. That becomes the range of my inverse function. The range, the output of my sine function was -1 to 1. Those are the sine function values that exist. That becomes the domain of my inverse function. Like we said, sine inverse is restricted from -π½ to +π½ because my inverse sine functions are negative in quadrant 4 and positive in quadrant 1. Remember when we do inverse functions that the input now, our domain, is the function value, and the output, or the range, is the angle. Okay, so here's a couple of examples we're going to work through. It says to find the exact value of sine inverse √3/2. So this is a function value. We're given a function value when we're given the inverse. We need to find the angle. So what this is asking is, what is the angle theta whose sine function value is √3/2? So sine of theta is √3/2. That's what we're looking for. Now remember, we were restricted to quadrants 4 and 1 for inverse sine, that original angle that we're going to get out. And sine inverse is positive in quadrant 1. So what is the angle in quadrant 1 that has a sine function value of √3/2? You can, if you don't remember it, you can look it up on your unit circle. It gives it to you here in the table, and you can see that that angle is π3, our special angle π3. Same thing as 60 degrees. Okay. Gives you a note. When an inverse is asked of an angle that we've memorized, we want that exact value. If it's not one of our special angles, we have to use our calculator and we would have to give an approximation. We couldn't give an exact value. So let's go to the second example. We've got sine inverse of 3/5. Now remember, I'm giving the function value and I'm looking for the angle. Well, 3/5 is not one of my special angle function values, so we're going to have to use our calculator. We know that because the sine function value is positive, the angle we get back is going to be in quadrant 1 because we've restricted sine inverse to quadrants 4 and 1. Now, we're going to use a calculator set in radian mode. So you're going to pull out your calculator and you're going to make sure you're in radian mode. And then you're going to use sine inverse. So your second function sine button gives you sine inverse of 3/5. And we're going to go ahead and round that to 2 decimal places. So in radians, the angle that I'm interested in, whose sine function value is 3/5, is 0.64 radians approximately. All right, and then we have another one. We're still going to be working with this in radian mode, but this time my sine function value is negative, which means that the angle I get back is going to be in quadrant 4, because according to my sine function restrictions, that's where my negative sine values are going to fall. It's only going to give me, now, yeah, well, let's just finish it and then I'll finish that statement. So sine inverse, I'm still in radian mode, of -2/3. Have to use my calculator because that is not a value for one of my special angles. Rounded to 2 decimal places is a -0.73, so 0.73 radians. Now, I want you guys to think about our unit circle. We have this sine function value for radians, -0.73. Let's say it's right here, correct? So this is angle theta whose sine function value is -0.73. Now, sine depends on the y-axis. It is also negative in quadrant 3. That means there is another angle that is this distance from the x-axis in quadrant 3 that also has that same sine function value. Why didn't we get both of those angles from the calculator? Well, because in our calculator, to perform our calculations, we have restricted our sine inverse to these 2 quadrants. It's only going to give you, if you start with a negative sine function value, you get an angle in quadrant 4. If you start with a positive sine function value, you get an angle in quadrant 3. For this first one, we returned an angle of 0.64 radians. Let's say that one's right there. That's going to be that value for theta. Well, that's not the only place where my sine function has a value of positive 3/5. Sine is also positive in quadrant 2, that same distance from the x-axis. Sometimes this is easier to look at if we consider our special angles. I have, let's do this. Let's do pi fourth has a sine function value of square root 2 over 2, correct? Well, 3 pi fourths also has a sine function value of square root 2 over 2. These angles are the same distance from the x-axis. So remember that there's always going to be two angles, but when I'm using my inverse function, I only get one, and that answer is the one that is in my restriction, depending on which function I'm interested in. So let's switch and focus on our inverse cosine function for a minute. Just like we started with our inverse sine function, we're going to start talking about the fact that we have a periodic function, a cyclical function. For cosine, it is not one-to-one because our domain is all real numbers and it would totally fail the horizontal line test. But if we sufficiently restrict the domain of our cosine from all real numbers, then we end up with a one-to-one function that has that restricted domain of the cosine is the restricted range of cosine inverse. Now, as I mentioned, cosine focuses on that x-axis, so our restriction on the inverse, if we restrict from 0 to pi, includes all of our positive cosine function values and all of our negative cosine function values that are possible. So for cosine, because it focuses on the x-axis, the restriction is from 0 to pi inclusive. And that shows that right here, from 0 to pi includes all possible cosine function values and none of them are repeated. So how is y equals cosine s inverse notated? Just like with sine, defined implicitly, we have x equals cosine y. We never work with it like that though. When we solve for y, we get the explicit definition that we use, y equals cosine inverse of x, where the domain of the inverse function is the range of y equals cosine x. So we've switched our domain and range. And here is this graph, our cosine graph, reflected to give us the cosine inverse. The domain of restricted domain of cosine becomes the restricted range of the inverse. And the output, the cosine function values that was the range of cosine, becomes the domain of cosine inverse. And if you guys hear the buzzing in the background, I apologize. Our neighbor is weed eating some serious yard space. Okay, so the output, the range output is the angle. The input is the function value, just like we did with our sine inverse. All right, let's keep going and do some examples for our cosine inverse. Finding the exact value. When I see exact value, I expect a special angle on my unit circle, so I can reference that, not my calculator. By definition, y equals cosine inverse x means x equals cosine y, or what I'm actually saying here is I want the angle whose cosine function value is negative square root 2 over 2, because that's what I was given. What's the angle theta whose cosine function value is a negative square root 2 over 2? Well, we said that cosine inverse is restricted to quadrants 1 and 2 from 0 to pi, and cosine is positive in quadrant 1, negative in quadrant 2. So we are looking for the angle in quadrant 2 that has a cosine function value of a negative square root 2 over 2. Well, that's my 45 in quadrant 2. So that's going to be 3 pi fourths. If you don't remember that, you can reference the table or you can reference your unit circle. If you don't, if it's not a value that shows up on your as your special angles in your unit circle, and now we get a plane flyover, then you're going to have to use your calculator and approximate. So here's some approximations we're going to find. Okay, the answer to cosine inverse of 0.6, that's not a value on my unit circle. It's not a special angle value, but it's positive, so we're going to get an angle in quadrant 1 because cosine inverse is restricted to quadrants 1 and 2. Using a calculator set in radian mode, we're going to use radian mode for both of these. Cosine inverse of 0.6, you're going to find that on your calculator just like we did sine inverse last time. We're going to do second function cosine to get cosine inverse of 0.6. It's positive. We get an angle, we're going to round to 2 decimal places again. My radian value for that angle is 0.93. What if I wanted it in degree mode? Well, all I need to do in that case is switch it to degrees, hit enter again, and it tells me that 0.93 radians is about, so if I wanted degree mode, I would get 53.13 degrees. All right, so in radian mode, find cosine inverse of 1.8. So if I do cosine inverse of 1.8, I get a domain error. Did I do that wrong? Well, no, I didn't do anything wrong. When I'm using cosine inverse, I'm inputting the cosine function value. And all of my cosine and sine function values have to fall from -1 to 1. So that value, 1.8, is outside what is my range of cosine, or the domain of cosine inverse. It's not a possible cosine function value. Okay. Use the properties of inverse functions to find exact values of composite functions. So this sets up what we know about sine and cosine inverse. Remember that if we take the composite of the two, we get x. So this is always true no matter which direction we do the composition, as long as that value x falls within our restriction. Notice that when I start with f of x on the inside, my restriction is the angle, because that's what I'm using. When I start with f inverse of x on the inside, my restriction is the function value, because that's what I'm using, x. That's what my input is, that x is. Okay, keeping this table in mind, let's reason through this next page. Now, we've got to really reason through this concept, think through the concept. And if what we do here isn't enough, you can watch my Math Lab videos on this section. You can look this up on Khan Academy. You can bring it up with me and collaborate, whatever you need to do to start reasoning through this concept. But as we move up your math pathway through the calculus pathway, you're going to notice that you're focusing a lot more on concepts and a lot less on memorizing steps. Okay, find the exact value of each of the following composite functions, making sure the answers are in the proper domain. So looking back on that last page, make sure they're in that proper domain. So we're doing a composition of sine and sine inverse. Because I'm on the inside, I've got sine of an angle. That's what I'm focusing on, is an angle value. If I take sine of this angle and then do the inverse of that, what it gives me is this angle, pi 12, because pi 12 falls within my restriction. On B, I'm starting with the inverse function. So I'm starting with a function value. That function value has to fall between -1 and 1. When I take the sine of the sine inverse, I get out that original function value of -0.4. Now let's look at C. I'm starting with an angle as my input because I'm taking the inverse of that sine function. So my question is, does this angle, 3 pi fifths, fall within my restrictions? It does not. So my answer here is not going to be 3 pi fifths because 3 fifths is bigger than a half. Half of 5 is 2.5, and 3 is bigger than that. So 3 pi fifths is going to be outside my restricted area. So it's going to be out here somewhere, which means we need to do a little bit of work to see what the angle is that I would get inside that restriction, okay? We're doing sine, so we're focusing on our y coordinate. 3 pi fifths is bigger than pi half. So pi half is here. That means 3 pi fifths is going to be, let's say here, this is 3 pi fifths. Well, if 3 pi fifths falls in quadrant 2 and it has a positive sine function value, there's another angle that has that same positive sine function value that falls in quadrant 1 because sine is positive in both of these quadrants. That other angle is going to be right here, and that's the angle we're looking for. What is that angle? Well, these two angles are the same distance from the x-axis. How far from the x-axis is this in quadrant 2? Well, this is pi, 0 to pi, and if I'm at 3 pi fifths here, then this distance from the x-axis has to be 2 pi fifths, because if I add these together, I get to pi. If this distance is 2 pi fifths, then this is also 2 pi fifths. So that is the value of the angle that I'm looking for, 2 pi fifths, because this answer is inside that interval. All right, let's look at D. 2 pi thirds. 2 pi thirds is between 0 and pi. So when I do that composition, I get out 2 pi thirds. E. Negative pi fifth. Is negative pi fifth within this interval? Well, no, it is not. It is negative. We're looking at cosine, so let's go look and see what this one's going to be. Well, negative pi fifth is going to be right here, right? This is going to be negative pi fifth. Cosine depends on the x-axis, and it's positive in quadrants. Oh, that's just wrong, isn't it? No, the angle is negative pi fifth. The angle is negative pi fifth. Cosine function value is positive in quadrants 1 and 4. So the angle negative pi fifth has the same cosine function value as this angle that's the same distance from the x-axis. This one's a little easier. This is just going to be a positive pi fifths. Positive pi fifths is the angle inside this restriction that has the same function value. So this answer is within that interval, not the negative pi fifths. So when you see these questions, you can't just automatically go, oh, it's this x, it's this x, it's this x. It is only this x as long as this value is within my restriction. When this value is outside of that restriction, I have to stop and look and see what fits. All right, what about f? Well, 0.6 as a function value fits, so that works. What about this one? Cosine inverse of 1.8. Well, I'm inputting a function value. 1.8 is undefined. It's going to give me that domain error. My cosine function values have to fall between -1 and 1. They're not going to be bigger or smaller than that. All right. Let's go on to our tangent and cotangent inverse. That's really the hardest part, I think, of this whole section, what we just went through. Once again, cotangent and tangent, we're starting with tangent, are repeating, periodic, cyclical, however you want to label them, functions, which means that they are not one-to-one over the domain from -infinity to +infinity. So we have to restrict that domain until we have a one-to-one function. We have to restrict that domain until we have a one-to-one function. Now, our restrictions, we could pick anything we wanted just about, but historically, we have an agreed upon restriction. Now, tangent is y dominant, and that's kind of a Campbellism. That's not something you're going to see in your book. But just like sine, tangent is what I like to call y dominant, because I have that y in my denominator for tangent. So my restrictions for tangent are going to follow my restrictions for sine. Do you remember your restrictions for sine inverse? They were from negative pi halves to positive pi halves. Our restriction for tangent, therefore, is going to be restricted to negative pi half to positive pi half, but notice that it's not inclusive. Now, when we did the restriction for sine function, we used brackets because it was inclusive. Tangent is not inclusive because those values at negative pi half and positive pi half are vertical asymptotes, which means we don't include those values. We include everything up to those values, but not those actual values. So how is y equals tan x notated? Well, again, implicitly, we have x equals tangent y, but we don't work with it that way. We work with it as y equals tangent inverse of x. Okay, and if I haven't gotten your notes adjusted yet, I struggle with adjusting these notes, but I will try. I don't think I can adjust this. This is a misprint. This should not be inclusive. It should just be less than, not less than or equal to. So that's a misprint. When you restrict tangent inverse, that is from negative pi half to positive pi half, not inclusive because of those vertical asymptotes. Okay, working down through our examples. Anytime I'm asked for an exact value, the implication is that I have a special angle that shows up on our table, on our unit circle. If I'm inputting negative square root 3 over 3, that's my tangent function value. I'm looking for the angle theta. So what angle has a tangent function value negative square root 3 over 3? Well, it's negative, so we know because of our restrictions that it's going to be in quadrant 4. Which of our angles in quadrant 4 has that tangent function value? Well, it is negative pi 6. All right, one last page, guys. Let's see. Now we're going to find the inverse function of the trig function. We're going to find the inverse, f inverse of f of x equals negative 3 cosine x plus 2. And notice that we've already set our restrictions. This is the domain of our cosine function, f of x. It is going to be the range of cosine inverse, f inverse of x. Because the domain becomes the range becomes the domain. We're just going to do a little bit of algebraic manipulation here. So the very first thing I do is rewrite f of x as y. Y equals negative 3 cosine x plus 2. Then I do my switch. I switch the variables. That becomes x equals negative 3 cosine y plus 2. Now I want to solve for y again. So I move my 2 over. X minus 2 equals negative 3 cosine y. And then I need to divide out that coefficient negative 3 so that I have x minus 2 divided by negative 3 equals cosine y. And now I've finished solving for y by taking the inverse of my cosine function. Now the inverse of the function just leaves me with y. So this becomes y equals cosine inverse of x minus 2 over 3, a negative x minus 2 over 3. Now that negative can stay in the denominator. It can go out in front of the fraction bar. If I distribute it into the numerator, I would need to change the sign of the x and the 2. So I'm either going to keep it in my denominator or put it out front. Now we've got to watch that negative. Let's go ahead and write it as in inverse notation. F inverse of x is cosine inverse of a negative x minus 2 over 3. Now, I gave you the instruction not to leave a negative in the argument. However, because of my restrictions, I'm not going to say, oh, you know what? Cosine is even. Cosine is even, but cosine inverse is restricted. Cosine inverse is not an even function because of that restriction, so we are going to leave it like it is. We're not going to mess with that negative when we're doing our inverse function values, all right? Okay, now, the range and domain of our inverse. We've already said that the domain of our function becomes the range of our inverse. So the range of f inverse is from 0 to pi, right? So from 0 to pi. But what about the domain? Well, we need to do a little bit of work on the domain. Our domain started out from -1, or the domain of our inverse. So the range of our function cosine, let me find a color here. The range of cosine is from -1 to 1, right? Well, range of cosine is from -1 to 1. That becomes the range, that becomes the domain of our inverse function, except I need to do a little work there. Because now I've got this argument instead of just x. So I start with that -1 to 1 business, but instead of x, now I have this x minus 2 over that -3. We're going to go ahead and leave that negative in the bottom so that I can deal with it a little bit more efficiently. X minus 2 over -3. So I want to solve this for x to get the domain of my inverse, my cosine inverse. So the very first thing I'm going to do is, to get that out of the denominator, I multiplied both sides by that value, -3. So this becomes 3 greater than or, and when I multiply by a negative, that inequality flips. X minus 2 greater than or equal to -3. Right? Okay. Now I've got to finish solving for x. I'm going to add 2. When I add 2, I get 5 greater than or equal to x greater than or equal to -1. So x is greater than -1 or equal to, x is greater than or less than or equal to 5. So my domain here is from -1 to 5. It didn't ask me to do, oh no it did, domain and range of the f inverse. Okay, makes sense? Let's do this last example. Solve tangent inverse of x for this given equation. So we need to first isolate tangent inverse of x. So what am I going to do here? Well, first thing, I'm going to add this pi third to the other side. When I add pi third to the other side, the right side of my equation becomes 3 pi thirds, or just pi. On the left, I've got tangent inverse x minus 5 tangent inverse x. That gives me a -4 tangent inverse of x. And I need to divide both sides by that coefficient, by that -4. So that gives me tangent inverse of x equals -pi4. Well, I take the inverse function. Taking the inverse, I take the tangent of both sides. And tangent of tangent inverse gives me x equals the tangent of -pi4. Now, what is the tangent of -pi4? It's going to be -1. The tangent function value of -pi4 is just -1.